You see this container? It is filled with gas. Now there is a piston attached to the container such that it can move up and down through the container without any leakage of the gas. Now, let's put some weight on the piston. I'm trying to apply some pressure. What do we see? We see that the volume of the gas decreases, or the gas gets compressed. If we put some more pressure, the gas will get compressed even further. Now that's fine. Now, if the change is isothermal, what does that mean? That means if the temperature of the gas remains unchanged during the process, then you will notice that the decrease in volume is inversely proportional to the change in pressure. That is, if you increase the pressure and make it twice, the volume of the gas would have got halved compared to the initial volume. Now, if we plot a pressure versus volume graph, we'll get a straight line with a negative slope. Let me get some maths into it. So we can say P is proportional to 1 by V, or P into V is constant. When the temperature was constant, isothermal, don't forget that. Now this law is known as Boyle's law. You want the name of the scientist? Robert Boyle. He was an English chemist who discovered this. Let's try to understand Charles' law. You see this container? It is filled with gas. There is a piston attached to the container such that it can move up and down through the container without any kind of a leakage of gas. If you notice, there is also a thermometer attached to the piston. We need that to measure the temperature of the gas. Now, let's heat the gas. What do we notice? The volume of the gas along with its temperature increases. Now, if you cool the gas, the volume will decrease. So what did we see? We heated the gas, volume increased. We cooled the gas, volume decreased. One thing that is to be noticed is the pressure on the gas is constant all the time. Now let's try to plot the change in volume of the gas against the change in temperature. And what do we get? We get a straight line with a positive slope. What that means is the change in volume of the gas is directly proportional to the change in temperature. So mathematically we can write V is proportional to T, or V by T is a constant. And the condition was the pressure on the gas was constant. This law is what is known as Charles' law. It was named after Jacques Charles, who was a French scientist who first discovered it. Let's solve an example using the mole concept. For that, we first need a question. Let's find the number of moles present in 110 grams of carbon dioxide. The first step is finding the molecular weight of carbon dioxide, which is simple. 12 plus 2 into 16, or 44 grams. So 44 grams of carbon dioxide is equivalent to 1 mole of carbon dioxide. So 1 gram, well, that's equal to 1 by 44. And 110 grams, that's our question. Simple, 110 by 44 moles of CO2, which is 2.5 moles of CO2.
Let us try to understand Gay-Lussac's law. Gay-Lussac experimentally studied the variation of pressure with temperature of a gas. Now let us consider a constant mass of a known gas at constant volume. When the temperature is increased, the pressure on the gas increases relatively. So what can we say about this? Pressure is directly proportional to temperature. So we can represent this as P is equal to KT, where K is the constant of proportionality. Let us now consider the temperature to be T1, where the pressure of a certain mass of a gas is measured as P1. For the same mass of the gas at same volume, but at temperature T2, the pressure changes to P2. According to Gay-Lussac's law, P1 by T1 is equal to P2 by T2. Now this law can further be illustrated by constructing temperature versus pressure graphs. Here, pressure for a gas is measured at temperatures 100 K, 200 K, 300 and 400 K. If all these points are joined, we obtain a straight line, which on extrapolation meets the temperature axis at 0 K. An interesting fact about atoms and molecules is that they are very small in size, but their numbers in even a small amount of any substance is very large. To handle these large numbers, a unit of similar magnitude is required. Just as we denote dozen of 12 items and score of 20 items, we use mole for microscopic entities. Let us define 1 mole. The amount of substance that contains as many specified elementary particles as the number of atoms in 12 grams of carbon-12 isotope, right? Now, the mass of a carbon-12 atom as determined by a mass spectrometer is 1.99 into 10 raised to the power minus 23 grams. Thus, the number of atoms in 1 mole is calculated as 12 gram per mole of C12 atoms divided by 1.99 into 10 raised to the power minus 23 gram per C12 atoms. So what is 1 mole? 1 mole is found to be equal to 6.022 into 10 raised to the power 23 atoms. The empirical formula of benzene is CH. It implies that carbon and hydrogen atoms combine in a ratio of. However, from experimental measurements, we know that the number of different kinds of atoms in a molecule of this compound is not just the lowest possible whole numbers. The actual composition of the molecule of benzene is given by its molecular formula. This shows that each molecule of benzene contains 6 carbon atoms and 6 hydrogen atoms. However, the atomic ratio is the same as the empirical formula. Hence, we can conclude that molecular formula of benzene is a whole number multiple of its empirical formula. We know that hydrogen chloride reacts with sodium hydroxide to form sodium chloride and water. Let us take a look at the chemical equation of the process. HCl plus NaOH forms NaCl plus H2O. We can make out from this chemical reaction that 1 mole of acid reacts with 1 mole of base to form, that's right, 1 mole of salt and 1 mole of water. We can also say that 36.5 gram of acid reacts with 40 gram of base to form 58.5 gram of salt and 18 gram of water. Now, if we take 36.5 gram of acid and react it with 20 gram of base, what will we obtain? We will obtain only 29.25 gram of salt. And why is it that so? It is so because even if 1 mole of acid is present, only 0.5 mole of base is present. Therefore, 0.5 mole of acid will remain unreacted in the resultant solution. Hence, in this case, sodium hydroxide acts as the limiting reagent, as it limits the formation of a product.
On your screen, you can see the formula for mass by volume percentage of a solution. It's simple. Mass of solute by volume of solution into 100. Volume of solution, that's important. Now let's take an example. We have a solution that has 20 grams of sugar in 400 ml of water. What is the concentration? In terms of the mass by volume percentage, mass of solute we know is 20 grams. Volume of solution 400 ml. Simple application of our formula. 20 divided by 400 into 100, and that gives us the answer as 5%. You see this formula? Mass by mass percentage of a solution is equal to mass of solute by mass of solution into 100. Now this is an intuitively simple formula. What is happening in this formula? Well, the mass of a solution, as you would have guessed, is equal to the masses of the solute and the solvent. So the mass of a solution is mass of solute plus mass of solvent, right? Let's take an example. Here you have a solution that has 20 grams of sugar in 380 grams of water. So shall we calculate the concentration in terms of the mass by mass percentage? Fine. Let's first write down the information that we have. Mass of the solute. And what is a solute? Well, sugar in this case is 20 grams. Mass of solvent, that is water, is 380 grams. So what is the mass of solution? Simple addition, 20 plus 380 or 400 grams. Now, let's use our formula. Mass by mass percentage of the solution is mass by solute by mass of solution into 100. Mass of solute 20, mass of solution 400, 20 by 400 into 100 or 5%. Simple formula, simple application.
While performing experiments on radioactivity, Ernest Rutherford bombarded fast-moving alpha particles on a thin gold foil. He observed the reflection of the alpha particles with the help of a screen. Now, according to Thomson's atomic model, an atom consists of a positively charged sphere with electrons embedded in it. So, Rutherford expected that almost all the alpha particles will pass straight and only small deflections will be observed if there would be any. However, Rutherford got totally contrasting results. From his experiment, he made the following observations. First, most of the fast-moving alpha particles passed straight through the gold foil. Second, some alpha particles were deflected through the foil by small angles. And the third point, some alpha particles were deflected by large angles. In rare cases, an alpha particle got deflected by an angle of 180 degrees. Based on his observations, Rutherford derived the following conclusions from his gold foil experiment. First, since most alpha particles passed through the gold foil without any deflection, most of the space inside an atom is empty. Second, very few particles suffered a deflection from their path. Now this means that positive charge occupies very little space inside an atom. Third and final point, as a small fraction of particles got deflected completely by 180 degrees, all positive charge and mass of gold atoms are present within a very small volume inside the atom. One of the major drawbacks of Rutherford's atomic model was that it failed to explain the stability of atoms. All moving particles radiate energy. In Rutherford's model, electrons revolve around the nucleus, so they should also radiate energy. This makes the electrons follow a spiral path and finally fall into the nucleus. Now, if this is taken to be true, every atom should be unstable. As a result, matter would not exist. It is for this reason that Rutherford's atomic model was rejected.
Let me show you a chlorine atom. What is the atomic mass of chlorine? 35.5. 35.5? But the atomic mass of a substance, if I remember it right, depends upon the number of protons and neutrons. Then it should be a whole number. How did we get 35.5? There is a reason. Let me explain. Chlorine exists in nature in two isotopic forms, 35Cl17 and 37Cl17. And it exists in the ratio 3:1. That means 75.4% of chlorine found in nature exists as 35Cl17 and the rest 24.6% exists as 37Cl17. When we have to calculate the average mass of the element, mass as well as abundance of all isotopic forms is taken into consideration. So the mass of chlorine is actually calculated as 75.4, that is the percentage, into 35 plus 24.6 into 37 divided by 100, which is 35.46. So the average mass of chlorine atom due to the presence of both the isotopes is 35.46. And don't forget, it does not mean that the fractional mass of one atom of chlorine is 35.46.